Hello and welcome to day number 5 of Labmas. And ladies and gentlemen, I am so happy you're here today. Now, in today's video, we're going to be learning a little bit about force, about motion, about laws of motion. We're also going to be having a special guest today that I cannot wait to have you meet. So stay tuned. Buddy, we're back again for day 5. You know, we might have failed the first 4 days, but today is our day. So before we begin today's video, I want to give a special thanks to all the teachers, to all of the students that have been reaching out to me, wanting to help with Labmas, sharing their experiments with me, as well as joining me in sharing Labmas with all of you. So if you're watching this right now, thank you to everyone. And a special thanks to Andy in kindergarten who sent me this incredible heart. Andy, miss you, buddy. And thank you so much. You have no idea just how much this means to me. And definitely give a big high five to your big sister at City. Let her know I miss her as well. So once again, ladies and gentlemen, thank you so much for the comments. Thank you so much for reaching out to me, and I hope you continue to enjoy the rest of the 7 days of Labmas. So today on day 5, what we're going to be doing is focusing on force. Now, force is a push or a pull. It causes things to move. All right. I don't know about you. I love to cause things to move, whether it's throwing a disc in disc golf or hitting a baseball while playing baseball or shooting a basket or just walking. Being able to move is one of the greatest joys that we have. And especially now that we're on break, we can do a lot more of it. Well, today's video and today's experiment is going to focus on the laws of motion. Now, real quick review. Ready? Law 1. An object at rest will stay at rest unless acted on by something else. Meaning, things don't move until you move it. Pretty much. All right? Also, things that are moving already will keep moving until something stops it. Okay? Law 2. Force equals mass times acceleration. The bigger something is, the harder it is to move, and the harder it is to stop. Law 3. My favorite law. For every action, there's an opposite but equal reaction. Meaning, if I drop a ball down, it's going to bounce up. Very good. So knowing those 3 laws for today will definitely help you with our experiment. So I'd like to bring out my guest today, and it's going to be Dr. Bryant of 3rd grade. So let's go head over to the lab and conduct a really fun experiment. Wait. Dr. Bryant? Oh my goodness, I think we're in trouble today. Oh no. You know what? We got this today. I know I'm all about doubt, but I don't doubt today we are not going to be able to do this experiment. Welcome back, ladies and gentlemen, to day number 5 of Labmas. Now today we have the incredible Dr. Bryant joining us.
Good evening, good morning. Whatever time it is that you join us, it's always going to be something fun.
All right. So today we're going to be analyzing and studying the laws of motion, and we're going to be using a couple different polymers to help us out. Now, as we learned in day 2 or day 1, which were day 2.
Day 2. Yes.
Balloons can be a great polymer. Now, what are some words that you would use to describe a balloon?
What's elastic, stretchy, fun. Let's see, they can suction too. So what would I say? You have to be careful with them as well. So they can be dangerous.
This is true. And ladies and gentlemen, these are all experiments that you should be doing with your family. Plus, that's the spirit of Labmas, ladies and gentlemen, sharing the love of science with everyone. So what we're going to be doing today is using these polymers to also show the 3 laws of motion. Now, as you saw earlier on in the video, we talked about the 3 laws of motion. Law 1, an object at rest will stay at rest unless acted on by another object. or in the same respect, an object moving will keep moving until it's stopped. All right. Law 2, force equals mass times acceleration, which is the bigger something is, the harder it is to move. And law 3, for every action, there's an opposite but equal
reaction.
Absolutely. So we're going to show that with 3 simple ingredients or materials. 1, we have our polymer. We have our balloon. 2, we have a cup. Now, I have found that the paper cups work surprisingly well.
Okay, paper cups.
Paper cups. And our mystery ingredient, the ping pong ball.
Yeah, so fun.
Now, how would you describe this ping pong ball?
It is round. It's hollow.
Is there a lot of mass?
It's light. Nope,
Yeah,
it's
there we
very
go.
light, so not a lot of mass.
So we should not have a hard time getting this to move.
We shouldn't.
So according to law 2, force equals mass times acceleration, we shouldn't need a lot of force to move this. But I don't know about you, I want to move this a long ways.
Okay.
So would I have to add more force to it?
Yes.
All right, we're going to do that, and the polymer is actually going to help us. So here is step 1 of our experiment. You go ahead and take your cup, now be careful, and you cut out the bottom of it.
And remember to use your safety scissors.
Yeah, these are not the safety scissors. We are trained professionals.
That's right.
Just kidding, I'm just kidding. But we are trained professionals. There you go. And you want to cut out the bottom. I'll let you go ahead and cut yours out. All right. Now, the reason why we want to do this is because we pretty much just want a kind of a cylinder where we can actually see through it. Because we're going to, well, let's just say the shape of this cup is going to help us add the force that we need to in order to get the ball to move. Okay? Now,
Extra out.
should be pretty good. All right, the next thing is we take our safety scissors, or in this case, our teacher scissors. And this part is harder than it looks, ladies and gentlemen. You need to cut the balloon in half. You need to take the top nozzle of the balloon off.
Wait, cut a balloon and a cup? What does he think he's doing? And people call me crazy.
So I'm going to go ahead and cut now. There we go. And like I said, you need to, I will cut it for you.
Thank you.
That will make it a lot easier. All right. So this top half, we don't need. We can just put that behind it.
Okay.
All right. Now the top, what's great, and Dr. Bryant said it earlier, it's stretchy, isn't it? All right. That's the great thing about polymers, ladies and gentlemen. They are stretchy.
And flexible.
And flexible. So what we're going to do is we're going to stretch it. So we're going to go to the opening that we just cut through, and we're going to stretch it over the top of the cup that we just cut.
All right.
All right. Now, you don't have to press it down or anything like that, because the great thing about polymers is they will usually stick, and just like we saw on day 2 where Miss Blake put the screws through. What's happening here is they're already making a seal to the cup. All right.
Look at
so
that.
yeah. So now what we're gonna do? This is the hardest part, guys. Ready? We're gonna take our ping pong ball and put it in the cup. Whew! I need a break.
Yeah, I'm tired. Do you have anything to drink?
I don't know.
Ooh, I worked up a sweat.
All my cups have holes in them. So here's what we're going to do next.
Okay.
We are going to add force to the ping pong ball, but not directly.
Okay, push and pull.
Now, if you remember law 3, for every action there's an opposite but equal
reaction.
So if I want the ping pong ball to go up, I need to pull my polymer down. So we're going to go ahead and pull our polymers in 3, 2, 1.
Woo!
Now, what just happened? Well, if you notice, when we pulled our polymer down, it had that elasticity, didn't it? But when you add force to the polymer, that force is stored and that energy is stored in it. So when you let go, it is going to retract to its original form, but that energy's got to go somewhere. Dr. Bryant, where's the energy going to go?
It goes to the ping pong ball.
And I'm going to tell you this right now, the harder you pull it back, the further it goes. You can also, whoops.
See, I'm going to aim for that. Let's see. I like Duke, so there's no Carolina for me to aim for, so I'll aim at the Hurricane.
Go.
Did you just see that ball fly in the air? You know, I think we're in real danger. We may have things flying at us. We better get out of here. Whoa.
Woo!
And if you
Awesome.
notice, it also created sound energy as well.
Yes.
All right. So in this one experiment, we saw that the ping pong ball would not move unless we moved it. That's law 1.
1.
Okay. This ping pong ball is light, so we don't need a lot of force to move it. That's law 2. And since we pulled it down to have it go up, that's for every action is an opposite but equal
Reaction, and that is 3.
Absolutely. So if you want to try this at home, I highly recommend it. It's very easy, but definitely get your parents' help, especially with the cutting. I want to thank Dr. Bryant for joining me today.
My pleasure, Mr. Scientist Sergeant.
All right, happy Labmas.
Thank you. It's been great. This is so much fun. It's so much fun.
Now, I want to thank Dr. Bryant for spending day number 5 of Labmas with all of us today. She did such an incredible job. And I think we had a little too much fun showing the different laws of motion. Now, this is a great tool to show all 3. Okay, let's do a quick review before we end the video. 1, this ball will not move until I add force to it. All right. Law 2. The ball is light, so I'm not going to need to add much force to it. So force equals mass times acceleration. The amount of force that I'm going to need to move this is not going to be much. And law 3, for every action, there's an opposite but equal reaction. I pull down, it goes, ooh, it goes up and almost hits me in the head. All right, so thank you, ladies and gentlemen, for spending another great Labmas with me and with Dr. Bryant and with everybody. So from GPA, the teachers, students, thank you for watching and stay tuned for tomorrow's incredible day number 6 of Labmas.